Hello, everybody. It's so exciting to be the speaker today. I titled my talk as AI and the public transit. This is really a collective work with a large group of people working with me for many years. First, I want to clarify what the talk is not about. Today, there's so much discussion on the large language model, so much discussion on even the sparks of artificial general intelligence. Even its spark, the fact that we can discuss AGI in the scientific way itself is alarmingly powerful. Along with it, the impact on the jobs, impact on education, the disinformation and fate of democracy, even the existential threat to human species. These are such important topics that in the future session, we'll have a designated discussion on these topics. But today, we will not talk about those areas. Today's topic is more mundane, talk about specific public transit operation, planning, and strategy. What are the transit analytical functions, right? If you start from this transit analytic and the core, think I go either up the offline functions that lead to the service planning, operation planning, which then change supply, or to the right, you do this land use, employment, urban activities which then change demand. So from both the supply or demand side, now we have this automatic data collection system from AVL system, automated vehicle location, to the automatic fare collection system, automatic passenger counting system, to bring this information from supply and demand to the core of the transit analysis. And then more and more, the field moving into a more real-time functions, including the real-time service control, service management that changes supply on the fly, or real-time customer information that can inform and guide the passengers better. That's a real-time customer information back to the demand. So that's the general picture. Now the question is how AI in general can hopefully enhance or improve several of these functions there. At our lab, we focus on three areas. One is the behavior understanding, then which then drive the performance analysis, and then from our side on the decision support. These actually cut through both the operational functions, tactical functions, and the strategic functions of transit system there. That's the first one. The second point is that public transit in the United States has much bigger issues than what AI can address. I don't want to claim that AI can solve everything. Far from that. There's a very limited contribution AI is making now. Hopefully, the future can make more contribution. I want to acknowledge that there's a broader set of issues out there. Today, we'll focus on more narrowly defined view of AI and its contribution here. So specifically to the left, I put the three, this is the classic classification methodology point of view on supervised learning, and reinforced learning. How does that impact different functions of transportation? For example, the first one is the distributed analysis. On the supervised learning, we're doing many of this research on aggregated demand prediction, and later on the individualized demand prediction. Really, at each individual passenger level, can you predict the next trip? Using this actual language model, N-gram model, which indeed is one initial component of later large language model. And the third one, that's the synergy between discrete choice model and deep neural network model. The last one is on the reinforcement learning. We're working on how to use reinforcement learning to really improve the operational control. That's the three categories. To the right, we also look at text mining, computer vision, causal inference, general AI, etc. So today I'll try to bring a flavor of all this different research. How do you position this, right? Put this into two dimensions. One dimension is this vertical one between the structured data and unstructured data. For a long time, transit agencies were able to use this typical relational database-based table format, numerical data. But more and more, we are able to digest, say, for example, language data, in the sense of incident logs or customer feedback, or computer vision, or images. So this is one dimension. The other dimension is in terms of the time horizon of decision-making, either from short-term decision-making to the long-term decision-making. And you can position the different research into different this quadrant here. Today, we'll give you a fly-through of the different type of research. I put them into 4 zones. The first one is on demand prediction. We call this a deep hybrid model. The first one, Jinhua Zhao will present on the urban imagery for demand analysis. And the second one, Jinhua Zhao will describe the graph-embedded urban neural network, use that to predict the transit ridership. Then zone 2 will be on the monitoring side, broadly defined, where Dr. Awa will present the computer vision application for public transit travel time prediction, and Michael Liang will present the work with Wuma on natural language model for transit customer feedback intelligence. Then zone 3 is on control. Joseph Rodriguez will talk about the deep reinforced learning for real-time time control. And lastly, we want to include the discussion on the ethics, particularly the algorithm fairness in the public transit demand prediction. For that, Jinhua Zhao will present. Now is the show of the students.
So my talk will be on deep learning and hopefully become increasingly popular in the field of demand analysis. However, existing work sits primarily on numerical data with some modest performance improvements. And considering the successful deep learning applications such as DALL-E Midjourney and the even more famous ChatGPT, what really sets them apart is not marginally improving model performance, but making the progress from 0 to 1 on the ability to process unstructured data. And in recent years, there are actually quite a few papers that suggest that images are predictive of socio-demographic properties. And what's missing here is the fusion of images and socio-demographics. This is important because we believe that the data sources are complementary in nature. And to demonstrate this point, deep hybrid models are designed. Next one. Conceptually, deep hybrid model has a crossing structure. Horizontally, a deep learning model is used to encode the unstructured data. And in this case, we use an autoencoder. Vertically, the socio-demographics are integrated into the deep learning model, forming a latent space that contains both sources of information. And then the latent space is used to predict the travel behavior. So next one, this is the model performance on 3 different behavioral indicators. The y-axis is the R-squared value, and each different colored bars represent only socio-demographics, only imagery, and deep hybrid models respectively. And we have auto, active, and public transport. We see that only imagery and only socio-demographics, R-squared is above 0. And our deep hybrid models can outperform both. Thanks to the latent space, which connects all the model components, we could also develop economic interpretation of existing and generated images. In this diagram, only S and C are real images, which represent south and central part of Chicago. The other images are generated by feeding a linear combination of the latent spaces of S and C into the decoder. On the image side, we could clearly see a transition from S to C, getting denser and then going beyond. We could also calculate the mode choice changes corresponding to the imagery change, which is presented above the images. For example, the auto usage drops when moving towards the downtown area with an increase in both public transit and active modes. The more smaller figures below show other economic quantities we could develop. Next one. In fact, the latent space is flexible such that we could not only move between 2 images, we could mix an arbitrary number of images and observe the socio-demographic and travel behavior implications. So this is a 2D illustration with we add another real image N representing North Chicago, and then the mode choice changes are presented on the right. So I hope I have convinced you that deep hybrid model is an innovative modeling approach that opens up many possibilities in demand analysis, and we'll be introducing another application incorporating road networks in the next section.
This is Dingyi. So my work is the extension for Qingyi's work using a urban road network as our input. So you can see that from this flow chart, you can see our input changed to the road network G, and right now we're using the graph embedding instead of the image computer vision. So we still learn the latent space integrated with numerical data like social demographics. Right now we do not have the generation part, but we're focusing more on the choice model to regress on the travel behavior. So the graph embedding can learn the representation of the neural network into a more low-dimensional Euclidean space. And this whole process actually came free from us from the feature engineering and prior knowledge and assumptions on the urban road network, like the density, device, diversity, etc. Next slide, please. So our case study is using the input data from Chicago, recording the road topology and travel distance. Apart from that, we also choose 1 year of social demographic information. So our test, I will show you how it will benefit to regress in the public transit mode share and also income per capita. Next slide, please. So what can this latent space do? Actually, you can learn, if we look into like 3 of our learned 128 dimensional latent space, you can see the first of 3 actually represent a very different perspective of the social demographic correlations. Next slide, please. So if we aggregate them in a spatial level, you can see the left one is the aggregated graphic embedding readouts, and the right one is the public transit mode share distribution. You can see that there's a very strong spatial insight and correlation between these 2. Next slide, please. And if we saw this aggregated latent space values, you can see that from the small quantile to a larger one, you can see in the transition that represented the row network structure. Yeah, the quantile means the value of the embedding results, and the upper row is correlated, the corresponding row structures. You can see that it transits from a sparser, irregular, and non-rectangular shapes into a denser, organized, and more graded counterpart. Next slide, please. And we go back to our regression performance. We use training and testing split of our 30% and 30% of the sensor tracks. Both our baseline models and our proposed model use a simple linear regression for the choice model, but our inputs are different. For the baseline model, we use the previous very classic feature engineering way. And for ours, we just only use our graph embedding vectors. You can see that from the right-hand side tables, both on account of both in-sample and out-of sample R-squares or improvement are all near or larger than 30% percentage.
Now let's move to the second block on monitoring. I'll invite Awa to start with the computer vision discussion.
Perfect. Hi, everybody. I'll be presenting on computer vision for transit travel time prediction. If you can go to the next slide, please, Jinhua. So this is a very familiar problem for everybody. You get to the bus stop, you see that your bus is arriving at some time, and the arrival time just keeps on changing because of the, transit is mixed with the other traffic that we really have no idea how to estimate the impact of that on travel time. And if we go to the next slide, we did this case study on this site in Mass Ave here next to MIT, where we have access to both the AVL data from the MBTA as well as access to our roadside camera. So the gist of this project was, if we move to the next slide, is to look into integrating the vehicle data, the AVL data, and the travel time data into annotating images. So integrating those different data sources that we have the advantage of in transit work for creating an end-to-end framework for labeling images to predict travel time. If you go to the next slide, big structure looks something like this. So we have 3 different data sources of real-time GTFS, a camera for image acquisition, and AVL data for labeling, and annotation of data. We train a vision transformer model to make those end-to-end predictions. So if you go to the next slide, this is an example of what we can see doing this. So after collecting extensive data, you can see at some normal conditions, rain, snow, or night, we see that the model starts to learn different features that help it deduce the underlying traffic state and hence create some anchor states that improve travel time prediction. You can see that it's really doing sensible things as learning that vehicle locations and queues at certain places affect the expected travel time, and things like at night when it can read the traffic signal, that also impacts the estimation of travel time. You can go to the next slide, please. We have different metrics of this. You can look at the preprint for more information, but what we can see here is the prediction from images into some predicted travel time discretized range as an anchor. And we can see that there's 4 different states of travel time. And we can see that by time, the model looks at enough images and starts to learn that those images map into certain expected travel time ranges that, if we go to the next slide, we can use as an additional attribute. So if we compare here just a very generic linear regression model that uses the time of day and historical data and direction of travel to anticipate travel time, it's not the most accurate if you can see the actual to predicted travel time on the axis. And this is what you're getting on your, constantly changing travel time estimation on a trip planner. But here, when we use those attributes, those anchor attributes that we get from images as an additional state estimator, we can see that this significantly improved the prediction ability of even a simple linear regression model. So we'll definitely look into more sophisticated models as we grow this project. And this is not the one application where we see integrating traffic data and images, transit data and images as something that leads into a functional application. But there are other cases, bus lane enforcement, the time that people spend on platforms and how that can be used to model and improve the estimation of dwell time and such, as really potentially good applications for vision and transit applications. And I'll pass it on to Michael to speak on the language side of things.
So I'm going to be presenting on a project that we very recently started with Omada to understand how natural language models can be used to understand customer feedback intelligence. The main crux of the problem on the next slide that we see is that in the current case, all the feedback data that comes from the web, from social media, from traditional comment cards, websites, even phone calls, comes in unstructured text. And right now, at most agencies, it's manually processed because it comes it's the rate it comes in is still able to be processed by humans. But the result of this is that it's difficult to discern these areas of concern or trends over time because we're looking at everything together. If we want to really gain a lot of intelligence, then in the next slide, we see that in an aspirational case, we want to be able to try to quantify this data statistics and automate a lot of these processes. So I'll give you an example on the next slide. We have 2 tweets, public information. And how should we try to label this data to quantify it? Well, I tried. And you can detect a lot of things, actually. You can have the mode, bus, specific route, stops, time, sentiments. You can even look at the gender based on the username or whoever submits the comments, right? But to do this at scale, that's when we are using the next slide. To do this classification task at scale, that's when we have to look at using different types of language models. On the left side, there's a distinction between unigram and n-gram models that are actually good enough to identify very, very specific things like a line or a mode or a route or someone's name. And on the right side, we have mass language models that are meant, it's a neural network architecture to predict context-aware words from neighboring words. And to actually uncover meaningful words for things like sentiment, sarcasm. And one thing that we were actually really able to do was we were able to train an in-house model to classify any tweet or any complaint into 10 very broad categories, very relevant to transit agencies, operations, customer service, cleanliness, and whatever not. Then we go to analysis, and then we see that once we're able to get these dimensions, then we can analyze over time what happens, right? So this is complaints about operations on the red line, and really two angles. On the left, we have proactive monitoring. When do we sound the alarm? For example, in this picture, it's when the amount of complaints goes over the moving 90th percentile. But then we can also look long-term at trends and policy analysis. For example, you kind of see a trend there. It's actually relatively stable, except there was a bump during COVID, mainly because this is complaints per million riders. So ridership went down and the ratio went up. On the next slide, we have an example of the questions we can ask for this. For example, did a deep cleaning initiative last year lead to less complaints about cleanliness? Well, if you plot the negative complaints about cleanliness per million metro riders over time, then you can see the significance of the effect, and it depends on how many months you look back and forth. On the next slide, you can also agglomerate them by bus routes, and then we can look at from here. You can imagine this as a dashboard. You would maybe be able to select what routes, and you can either bring up all the complaints, or we can ask our friend ChatGPT, what do the complaints say? And you can see that on the next slide. We can summarize, well, what are the main causes of the complaints? What are the impacts to the customers? And even what did the customers suggest WMATA needs to do? The last two dimensions in particular are ones that we can only uncover after looking at feedback. So to sum this up and to zoom out, how can we use the unstructured data to improve transit operations? Really, what I'm really optimistic about is being able to combine existing measures that are absolute and numerical, like frequency, accessibility, whatever not, with future measures that are more abstract, perceptual, emotional, to really lead us towards more responsive operations.
So hi, everyone. I'll be talking about how we applied reinforcement learning to improve bus service reliability. Next, please. For a bit of context, so the problem of bus routes that operate at a high frequency and in mixed traffic is that they're subject or have a strong tendency to bunch, and which is what you see in the photo and the diagram to the right. Next, please. And the problem with that is it makes bus service unreliable, overcrowded, and requires riders to over-budget travel times. Now, there are some strategies you can implement to correct for this, like bus holding and stop skipping. And you can make use of several criteria that can be decision rules, optimization, or even reinforcement learning, which this research focuses on. Next, please. So to give you a sense of what the problem looks like, on the left, you see kind of a bus line, a lot of buses, and this is a unique type of control system because you can only make those control interventions at a specific time and location, right? Only when a bus passes by a certain checkpoint. And so this doesn't fit well with the centralized control framework, but rather more intuitively on decentralized control. And the proposed approach is to a certain extent, centralize the training by sharing information between agents that are close by and can affect each other. Next slide, please. And how we do that, you can see a snapshot on the right of a control step, and you focus on the trip in the middle, that when it arrives at a checkpoint, it selects an action, which is going to be evaluated only when the experience of the riders using trip I or trip I+1 has materialized. And so in that way, you expand the scope of the reward. And in the rest of the ensemble and the environment model, we support this kind of expansion. Next. Now, we have trained the model and tested it in simulation. And we have also actually applied a simplified version of this to an actual field experiment in Chicago. So we took the reinforcement learning recommendations to adjust the departures of a bus route in the north of Chicago, bus route 81, over 1 week. Next slide, please. We've looked at the performance in terms of metrics that are of interest to many stakeholders like riders, drivers, agencies, and cities. And the improvements we see are, for example, for riders, excess waiting time was reduced significantly, and things like crowding and cycle times, and as well as linking back to the Department of Energy grant or project, we have computed the mobility energy productivity score for the area of this bus line, and we have observed a significant improvement in that sense as well.
I just want to add one word of thank you to our colleagues at Chicago Transit Authority. They really offered a systematic support throughout the institution for Joseph and our team to really implement this IO-based idea. So it changed from just being an idea in the simulation to actually on the ground seeing the impact in practice. So next we'll move to the last module on algorithm fairness by Yunhai.
As a background information, machine learning has been widely adopted in many applications. However, many recent studies have found that the machine learning model can produce unfair predictions against the disadvantaged populations. So in this study, we want to investigate whether the fairness issues also exist in child behavior predictions, and if so, how to mitigate them. Next slide, please. So one widely used criteria for machine learning, for fairness in machine learning, is equality of opportunity, which requires that the predicted outcomes, such as child behavior indicators, should not be influenced by sensitive attributes, given that the actual outcome is positive. So to achieve equality of opportunity, it is crucial to ensure that there is a minimum difference in the rate of false negatives between two social groups. Next slide, please. So our study shows that fairness issue widely exists in child behavior prediction models, whether using binary logistic regression or deep neural networks. So the two graphs here show the disparities in false negative rates between racial groups when using the binary logistic model and deep neural networks. As shown on the left figure, significant differences in false negative rates exist between ethnic minority and majority groups when predicting frequent usage of various travel modes using the binary logistic regressions. And the graph on the right shows that although the adoption of deep neural network has considerably reduced prediction errors, fairness disparities still exist, with similar signs of disparities as observed in the logistic regression model, except for biking. So after acknowledging the prevalence of prediction disparities among different social groups, we implemented an absolute correlation regularization method to mitigate the prediction bias. So we incorporated a regularization term into the standard cross-entropy loss function during model training. So this regularization term basically penalizes the correlation between the predicted outcome and the sensitive variable z, given the true outcome. And the hyperparameter lambda here controls the trade-off between accuracy loss and fairness loss. Next slide, please. So here we show the results of applying the bias mitigation method to the predictions in terms of both fairness and accuracy. The graph on the left illustrates the impact of increasing the regularization weight on prediction disparities. And two lines here are trending downwards, which shows that our method is effective to mitigate the prediction disparities for both binary logistic regression and deep neural network. However, the graph on the right indicates that as the bias mitigation weight increases, the model's accuracy also decreases, which shows that the improvement of fairness comes with a cost, and there is an inherent accuracy fairness trade-off when mitigating prediction bias. Okay, so I'll turn it over to you, Jinhua.
Thank you, Yunhai. So hopefully that's give you a flavor of all the research that's ongoing in the lab. Last, I'll just say a few words about some of the future project that we're contemplating. Here's a few examples. The first one is to really introduce the form of causal analysis empowered by the machine learning. For that, Jinhua actually working on some example of that. Second one is using the generative AI in the urban images for us to be able to really realize the imagine the cities or transportation system. And also we have some work on the future of jobs in public transit, how the definition of a job of being a bus driver will evolve over time, given the different societal trend. And lastly, is on the multi-channel view of cities. I will just give the last, a flavor of the last point here. I want to mention that this Shenghao Wang is the thought leader on this. Shenghao we've been discussing this idea of how do we really describe cities, right? If you look at MIT as an institution, you will find at least 10 different disciplines all claim cities are their research subject. I'll give you a few examples. So if you are more design-oriented, say architecture, say I study cities, urban design, I study cities. And for this type of discipline, what's their data? What's their tool of vocabulary? We use images, right? Then also another type. If I'm an urban historian, I'm a sociologist, I use language. I write books about cities, right? So my vocabulary is a natural language. And then if you are economists, you probably use mostly numeric data, using statistics to describe the city. Well, if you're a transportation person or any other, you use graphs. We will build neural networks. You can see that different disciplines, they all study cities, but they really have a different style and they have a different vocabulary to describe things, right? What I end up is when we try to interact with each other, we do not have a coherent foundation, and we often talk over each other, right? So this is what Shenghao has been giving the analogy on. This really applies to this algorithm of the cave, right? We only see one particular projection of the city given your perspective. Like look at Chicago example, you may look at numerically the population, the auto ownership. In the graph, you can look at the transit network. And if you look at the image, you can, as a design perspective, or you can look at the natural language from the books or Wikipedia, etc. Right? So now the question is it possible for bring them together? For example, in a typical prediction setting, let's say predicting car ownership, you have this certain X as an independent. So it's the preventative owning a car is a function of a whole set of numerical variables, right? But can we generalize the idea to include new numbers, images, languages, and graphs, all as a meaningful input to this exercise, right? So DNN seems to provide a potential unifying framework to process this multi-channel view of cities. Right? Hopefully we can get to the degree that we have several dimensions that all can look at the city as an object so that the discipline can really talk to each other in a deeper connected way in this. What Dingyi and Jinhua presented some flavor of this, how to incorporate images, how to incorporate graphic network, road networks, how to incorporate languages into this. Now that attempt has been isolated, right? But the goal is, can we actually put this together as one unified form of this, right? So this is what we present. And then also to mention that we're just starting a project with Singapore, more fundamentally look at how AI will empower people, institutions, and city that hopefully can address the initial question that I raised at the beginning, go beyond the public transit. All right, thank you, everybody. I'll now pass forward back to Zhao.
Thanks so much, Jinhua. Look, before we get into the specific questions, I would like to just pose a question. You know, we have a number of folks on this forum that are not public transit professionals. What is it that the non-transit professionals need to understand? What are the observations that you have in working directly with some of the public transit agencies around the world? Like, will we really see this future where AI can, for example, enable predictive analytics so that the system can truly be more responsive to the living demand patterns of a city? I mean, to put it very simply, if I head to a basketball game at the TD Garden and there's just no train available coming out of that to head back, we know that these basketball games are taking place. Do we actually see a future where that sort of analytics is really incorporated into public transportation networks?
First of all, transit exists for two arguments. One is the density argument, the other one is the equity argument, right? The density argument is saying that given a high density urban development, transit is the only form of transportation that can enable such a high throughput and therefore enable productivity and urban creativity in that. The second one is an equity argument, right? That's to say that for a certain group of people, for many of them, public transit is their lifeline for mobility there, right? So both roles are important here. Another important thing I want to say, at the beginning I mentioned that the state of public transit in the United States now has a much bigger problem than what AI can address here, right? If we couldn't have bus drivers run the train, run the bus, if our signal system is falling apart, it doesn't matter how our AI fantastic thing we're doing here, right? We're of course looking at this is analytical part. Hopefully several of the examples we plan can make this a specific contribution to improve prediction, improve monitoring, improve the customer experience, improve the control, right? But how the system will work together, can we have a meaningful both political support and a financial support and operation support? That's clearly beyond what AI can do there.
I just want to provide some general discussions we have for all the presentations and students just present. Based on my observation, I could see actually three tensions in this AI and plus public transit research. The first one is really the tension between computer science and all the other domains. Because as we see that like deep learning and AI is permeating into all the other domains, and people just start to question whether the other domains have the independent like academic values. And actually, through those deep hybrid models, we do provide one answer, which is we should create a more positive dynamics and adopt a more synergetic perspective, and then try to not only adopt some AI technology and apply them to a specific domain, but have the like backward feedback, like using the domain knowledge to enhance as an AI the specific models. So that's pointing to the actual motivation underlying and the Dingyi's work. And the second tension is actually from Joseph's work. That's the tension between state of the art and the state of practice. So because Joseph actually in his work, he really developed state of the art, deep reinforcement learning for the transit control. But when we really implement that technology in Chicago, we kind of intentionally keep the gap. We cannot like use the most advanced technology, but really simplify that and then implement the technology to create a more robust workflow and then demonstrate the social impacts. We believe that gap between state of the art and the state of practice is a healthy and desirable gap. We need to protect that. And the third tension is actually between the private and the public sectors. Remember, the public transit is really a public sector. So when you think about the application of AI technology, now most of the technology is still just like maximize the prediction accuracy. That's a simple like single object optimization, which can be easily adopted in private sector, in which the profit usually is a single objective. But whenever we go to public sectors, the objective become more complicated. It's not only just a profit, but many other aspects like equity, fairness, also like a basic accessibility. So we believe that recent trends in AI, I talk about the ethical aspects, transparency, interoperability, and fairness for the AI technology is really important, especially in terms of the application of AI in public transit. So that's the fundamental motivation for Yunhan's work.
Let me briefly offer some observations in response to John's question. I think there are some interesting applications, especially at the intersection of what we've called zones 2 and 3 in today's schedule. And Jinhua mentioned the severe workforce shortage that transit agencies are facing, not being able to run 20% or 30% of the trips because the drivers aren't there or have quit or aren't being hired quickly enough. But also on the dispatch side, we're lacking dispatchers. That's especially acute here in Boston because trains to be run at much lower frequencies. So how do we break that cycle? How do we make it less stressful for dispatchers? How do we let them do their jobs more effectively to mitigate some of the short-term problems we're facing? I agree with Jinhua. AI is not going to solve the fundamental problems facing public transit, but I think there are substantial opportunities to mitigate some of the acute issues. So what would that look like for operational control and dispatch to mitigate some of this workforce shortages? I could be giving dispatchers alerts, right? What are the top 3 things they could do, in a given period of time to improve service for the most amount of people? It could be kind of suggestions, alerts. I think these would also incorporate the unintended consequences that control actions might have. So dispatchers, especially newer dispatchers, people dispatching buses or trains, might be pretty reluctant to make any sort of service intervention because there could be unintended consequences, and there is a lot of underlying unstructured complexity in terms of labor rules, downstream effects, network effects, etc. So I think there is great potential here for AI. Instead of needing, 2 decades of on-the-job learning for a dispatcher to feel comfortable making a recommendation, there's an opportunity here for AI and ML-based tools to kind of do that learning quickly and then offer recommendations for dispatch actions. So I'm excited to see some of those applications, and I look forward to hearing other people's reactions to those.
Super. Okay, that's very helpful context. I'm going to turn over to Bhuvan right now to take us through some of the questions in the chat.
Thank you, guys. This has been also our largest forum. We've crossed 450 attendees. So great job, great presentations all. And you've made my job tougher by answering a few of the questions in the chat. So I've been struggling to keep track of what has been answered already and what has not been answered. But let us give this a shot. So a couple of the questions, were general questions related to the applications of AI in public transit. A couple of the questions, were very, very specific to a particular project, which most of you all seem to have, I think, covered in your project. So there was one question, I think, to Avad on the bus travel time predictability project. So Brian Bonner asked if, with the increasing, battery electric buses coming into the fleets across various transit agencies. So was that considered as one of the inputs in your model, and how may this affect, the travel time prediction and reliability for the model that you had developed?
Yeah, this is a very good question. I tried to answer part of it in the chat, but I think it's also more important the other way around, honestly. So what we looked at in this project is what does the overall state of traffic look like and how that maps into predicting travel time, and not the impact of the exact type of bus on that, because the bus is just a component of that. But I think to the point, I think when it comes to electric buses, it's the reliable travel time prediction that we're talking about now is more from giving reliable real-time information to passengers, updating it with what we can see, right? Seeing the traffic. But I think for battery electric buses, it becomes even more important than just giving reliable real-time information, because you plan blocks based on that. You have your run times based on that. It's much more impactful when you're talking about batteries. When we talk about things like the anticipated traffic state and how that affects the starting and stopping, that has a huge impact on regenerative charging for electric buses. So I think the impact would be more on how can we reliably, model traffic state or estimate traffic state from images to help us plan for buses. And then, maybe there is a role that when the bus is electric, travel time is affected, but it's definitely affected more by the general state of traffic.
Okay, thank you. So there was another question actually on electric buses from Sunil Nair from the MTA New York. So this was more a general question. So Jinhua, feel free to add in. So based on his question was more that, is there any work being done on including AI for predicting the performance of battery electric buses, tracking each, the state of health of each cell, when does it need to be charged, when, what is the state of the bus, how much can it run, things like that. So is there any research being done in that space to use AI to, get the maximum range, get the maximum, service and minimum turnaround time for electric buses?
Sure. Yeah. Thank you. So there are multiple stages AI could apply in the whole kind of supply chain of this process. For example, using AI to fine tune the battery control system, right? That's clearly area literature work on this, right? I think more the operation side, one thing I want to introduce is so far, because often the battery-based bus cannot travel as long as the diesel one in one charge, right? So therefore, sometimes many agencies have to prioritize the electric bus deployment in the bus lines that have a short turnaround. So you can go in this one charge, right? But then when we get to the stage where we electrify at scale, then we're talking about all the lines need to be electrified. What this means is the transit planning process, like a vehicle scheduling, crew scheduling process, versus the charging process can no longer be thought of as a segmented, as an isolated process, right? You have to integrate the two. That's the area I think a lot of the current literature is going on to this, right? Combining the optimal charging problem, also together with this, your garage design, your battery design, these type of things, along with your vehicle scheduling and crew scheduling process, that raises a much complex either optimization problem or control problem. That's another area obviously AI can clearly be very helpful.
Thank you, Jinhua. My next question will be to Michael. So Nigel Waters, made this comment that sarcasm may be culture and context specific. So it's very hard to determine even probably for AI. So, sarcasm that, in the UK is very different from what passes off for sarcasm in the US, for instance. So, when you're like doing NLP and trying to get sentiment analysis of the various Twitter posts on, on public transit, good or bad, how does your model, cope with this sort of different global context of sarcasm and other, traits, behavioral traits? Thank you.
Yeah, no, that's a great question. Thanks, and that's something that we've been asking for quite some time. I mean, currently the way that we determine whether something is sarcastic is whether there is a contradiction, whether it's a model of the text, whether there is an irony inside. Did someone say something and something else in the same tweet or the same sentence? And an irony is something that is pretty universal across everything that is sarcastic, right? So if you see that tweet, for example, I had a great start to my morning when the train was dirty, right? That does not make sense, right? In terms of local specific captions, local specific expressions, for example, right? When we customize models to different agent areas, we can pick up a lot of these. We should be able to pick up a lot of these colloquial languages based on the context of the area, but that has to be something that you tune for every single area. So right now, this model only works. I'll say it works in DC, and it can be generalized to other places in terms of raw, but then that local context is what you miss.
Okay, thank you. So another question would be, I guess, on AI and dynamic routing. So, Mitch Erickson has this question on what happens when we take the cost of driver out of public transportation. If you have autonomous, smaller shuttles running with fewer individual dynamically routed vehicles. So how does AI play a role in optimizing this? And is this a method, to address the algorithmic fairness to get transit into areas where public transit is currently lacking in certain areas of, say, Chicago or Boston, for instance? So can we see AI playing a larger role here in ensuring a better transit reach in cities?
Good, thank you. So here I have to say that AI per se doesn't guarantee a value judgment. You can use AI to offer a very equitable service. You can also use AI to ensure equity, as what Jinhua just demonstrated. You can enforce equity constraint. And also we illustrate that sometimes you have to pay a price on efficiency. But let's be explicit about it. If we're serious about equity, that's the amount of efficiency we're willing to suffer from this, right? So here to say that AI application per se relate to my initial point about this alignment problem, right? Of course, routing, transit management, on-demand services is our domain, but this is a generic question, right? The biggest problem today in AI field in general is the alignment problem. Is how do you align this capacity that we demonstrate growing up and up every day with the human value, right? So transit is actually a good example to illustrate because there's so much attention attached to this field between efficiency and this equity, between the public sector and the private sector. Jinhua mentioned at the beginning, if you look at, suppose MIT develop an advanced prediction algorithm, control algorithm, right? Uber can read a paper, 1 week later, implement it, right? Can MBTA do that, right? So that's create a gap between both the innovation capacity of AI, but also the implementation capacity. So therefore, I feel like MIT as a research institution, we have a duty to balance the two. So that's why we emphasize quite a bit of application in the public transit sector so that we enough knowledge for the two field to more kind of a balance in that. One more thing I also want to add about the autonomous driving, right? For that, I think if you really discuss the public transit sector, the key question is what do I do as a driver, right? There's a create labor union issue and a future job issue. For that, we have a separate line of research looking at what's the definition of the bus driver may evolve into the future. For now, being a bus driver, what you do is navigate the vehicle, right? But with the automated bus system coming, the job may be less about navigating the vehicle, but is to interact with the passengers, right? To have a good experience with the passengers, particularly in today's public transit system, we have homeless, violence, mental health people, etc. Those are a new requirement of the bus driver that need to deal with, right? So bus driver is not that being replaced, their job will need to be redefined.
Yeah, I think the bus driver currently is juggling so many multiple duties. Their task is so tough. AI may make that task a bit easier by, taking some of the attention from the driving bit to other aspects of, running the bus service. That's a great point, So John mentioned this bit, about, how likely it is that transit authorities can, actually adopt some of these technologies. So, my question is probably to Joseph as well. You did the pilot for 1 week on Route 81. And there were good results. So is CTA, extending this technology to other routes as well? Because, there is a dire need to, do better predictions and, reduce headways in certain places. I took the Green Line on Wednesday night, and this was at 10 p.m. when both the Red Sox and the Celtics games had ended. And I can tell you my transit time took twice as long, and there was not even standing room in the Green Line to head back to Government Center. So there is, like John mentioned, these are things which everybody knows that the game ends at 9:30, but can we run more Green Line service, towards Government Center or Park Street? But transit authorities are struggling to even do the simple rule-based optimization. So how probable is it that, the AI-based optimization is implemented on a large scale, in the near term?
Yeah, if I could jump in on this, there's definitely an appetite on the side of Chicago to extend this to a decision support tool that they can use in multiple routes. But I would argue that AI would come in at the point where decisions that are currently made by different people, different groups of people, like different strategies such as altering the departures or short-turning a bus or expressing, they're all reliant on the intuition of several non-coordinating human staff. And so the potential of AI is to bringing this information together and sharing a platform where the decisions can be a bit more coordinated.
I also want to add that in terms of the big organization, their response to AI in general, and this large language model in specific. Let me give you one example. I was in Spain, we're talking to one of the corporation. They really are in a dilemma. What they told me is if my company do not engage with ChatGPT or equivalent, my competitors may engage them, have higher productivity than me very quickly, right? Particularly for this mundane business processing stuff, right? But if I do engage, then whatever of my own domain-specific knowledge will be absorbed into this general model, right? The first week it helped me, the second week it helped me, the third week it become me, right? So how to protect my intellectual property, particularly domain knowledge on this, right? I think this is actually a generic problem many of these old corporations are facing today.
Super. Just in the last 2 minutes, I'd like to turn the conversation back to you, Jinhua. We've talked about technology, and of course, you and your lab looks a lot at technology, but you also look at human behavior. And so I'd like to just close with any reflections you may have about the behavioral dimension. You know, what have you learned about nudging people toward public transportation? You know, this ID that I have on the back, it has free access, free quote for MIT staff to use the local MBTA system here. Do you see more of those types of programs that are about, you know, people and institutions? Let's put technology aside. What observations do you have?
Sure. Oh, thank you for the question. Indeed, my lab has kind of two prongs. One is this computational angle using this technology, using AI. The other one is the behavior angle. You try to have a more in-depth humanistic understanding of why people move, what motivates people here, right? So thank you for actually prompting that question. And then let me offer a behavior perspective of AI. Actually, the two are not separate things. First of all, how AI is being applied in influencing people's behavior. Then secondly, how behavior can help improve AIs, right? The first one, how AI applied to influence behavior. For that, social media companies are the kind of brilliant applicant of those things. They hire the best computer scientists, best psychologists with a single purpose for you get addicted to the social media. That's a clearly behavior intervention, right? But the other side, of course, you can use this in a very positive way, right? You can use this computational tool to empower many of the behavior insight we have, but just not to do more social media, instead to use more, say, sustainable travel, use bicycle, walking, and public transit. That's one aspect. The other aspect is I also have to say that the behavior understanding can also help us improve AI, right? That's where, for example, MIT, the cognitive science and brain science department are working very closely with the computer science department. The two fields are really mutually helping and benefiting each other. So many of the AI experts, actually, when they develop AI, some of them for application purpose, some of them, the intention is by building AI, I can understand the brain better, right? So that's a very different perspective on this. Overall, as you introduced at the beginning, my lab is try to bring the behavior thinking and computational thinking together in order to decarbonize the mobility system.
Excellent. Okay, and with that, we will close today's session.